Hi guys, this video is going to explain the process that takes place in bacterial E. coli cells when they are looking for and breaking down food for energy. Like humans, bacterial E. coli get hungry and need food for energy, but they can't just walk to market or Primanti's to eat. They need to be able to adapt to their environment quickly and eat whatever food is available around them. So for starters, E. coli prefers to eat glucose over anything else. It's like the ice cream of the bacteria world. Glucose is the best sugar for the job because it can be used as energy right away. Other food sources, like larger sugars, need to be broken down into glucose before they can be used as energy. Breaking them down requires energy and takes more time than glucose does, so lactose is more like a big turkey sandwich.
So, what happens if glucose isn't present around the E. coli? They're hungry, and without food, they'll starve to death. In this case, E. coli uses lactose, a larger sugar. Switching food sources like this is a complex process of gene control involving something called the Lac Operon, which we will explain by relating it to a typical lunchroom market central.
So if you think of our cafeteria as a bacterial cell, the Lac Operon is the sandwich station. If Market can get students to eat ice cream instead, it's not necessary to keep this station open, saving Market time and energy and giving students a nice sugar rush to get all their homework done quickly. So a student with ice cream is our glucose. Cheap, energy efficient, and readily available. However, if in the absence of ice cream, Market will have to supply students with sandwiches to fill their need for food. So a sandwich-eating student is our lactose. Now, to start the process of getting and eating sandwiches as a student, we first need the station to be open.
Again, normally the operon is not actively working. A repressor molecule blocks RNA polymerase from binding to the operator area in the promoter site and starting the transcription of the sandwiches. RNA polymerase can only start transcription if the repressor is removed. This situation is called negative repression because by default the Lac Operon is turned off. Also makes the Lac Operon an inducible operon, whereby another molecule called the inducer switches the operon on. In this case, our inducer is none other than allolactose, a slightly modified lactose. Once the inducer removes the repressor, RNA polymerase, also known as polunculatase, can begin transcribing the genes into mRNA that will eventually be made into specific activated proteins.
There are three coding regions on the Lac Operon that we are interested in: LAC-Z, LAC-Y, and LAC-A. LAC-Z is the gene that codes for the mRNA necessary in producing beta-galactosidase, which helps break down lactose into glucose and galactose. LAC-Y codes for the mRNA needed to produce galactoside permease, an enzyme that transports lactose across the cell membrane into the bacterial cell. LAC-A codes for transacetylase, which is also necessary for the cell, but we won't worry about it for now. In addition, the operator area is coded for by a gene called LAC-O, and another gene called LAC-I is located upstream of the operon and can shut down LAC-Z and LAC-Y if the cell can't find any lactose.
As RNA polymerase begins cranking out sandwiches using the ingredients LAC-Z, LAC-Y, and LAC-A, students begin to take them. Some would pick up the beta-galactosidase sandwiches and become lactose. Although it's slower than ice cream, this sandwich will still give the student enough energy to do some studying. Another specific worker picks up the permease sandwich and goes to the entrance of Market to swipe in more sandwich-eating lactose students.
Finally, the E. coli bacteria has all the enzymes it needs to provide a non-ice cream energy source. However, there is one more step in this process. What if both ice cream and sandwiches are present at Market at the same time?
There are two proteins in the bacterial cell, called CRP and CAMP, that come together to form a receptor protein. This protein must be bound to the DNA or RNA polymerase cannot do its job. This is because the receptor protein opens up the promoter site for RNA polymerase, making it easier for it to transcribe the necessary enzymes. Think of this CRP-CAMP complex as plates and silverware. Even if a lactose opens up the sandwich station, nobody would get any sandwiches if there were no plates to put them on. With glucose present, Market doesn't put out as many plates for sandwiches, and fewer sandwiches are made as a result. This way, the cell will only use glucose until it runs low, at which point it produces more CAMP plates and hands out more sandwiches. In other words, when ice cream is plentiful, Market brings out fewer plates. When ice cream is scarce, Market brings out more plates. This process is considered positive control of the Lac Operon.
Now let's see what happens when we start making changes to the system with mutations. Say our negative regulation caused by the repressor breaks due to a mutation in the repressor. Now with nothing to stop it, RNA polymerase will always make sandwiches, even without the help of an inducer. If there is a defect in the LAC-Z gene, the cell will be unable to produce beta-galactosidase to ferment lactose. The sandwiches will then not give the students the energy they need because they cannot be broken down into glucose and galactose.
If there is a defect in the LAC-Y gene, the cell will be unable to create the permease needed to let lactose into the cell, and it won't make allolactose either, so there will be no inducer to activate the Operon. If there is a defect in the LAC-O gene, the repressor will not recognize the operator as a binding site, so nothing will stop RNA polymerase from transcribing mRNA all the time. This is considered a constitutive mutant. The operon will make the necessary enzymes to process lactose even when it isn't needed. The same can happen if LAC-I is mutated, or LAC-I might be mutated so the repressor cannot be bound by the inducer, permanently blocking transcription from occurring.
Now you know how the process of gene expression works when you're talking about bacterial cells. Bacteria can switch food sources based on what is available by expressing different genes that encode for specialized proteins. Glucose is the preferred food source, but the Lac Operon region of DNA allows bacteria to use lactose for energy when needed. The operon is normally turned off, but the presence of lactose, specifically allolactose, turns it on. If glucose and lactose are both present, the CRP-CAMP complex will allow the Lac Operon to work more when glucose levels are low, and less when glucose levels are high. This complex process has worked well for bacteria over millions of years, making them some of the most plentiful and successful organisms on the planet. Thank you for watching this video. Thanks to the staff of Market Central for letting us film there, and hail to Pitt.